So let's come back to the lecture. Now, having learned the language of vectors, we are now ready to discuss about two-dimensional or three-dimensional motion. We describe it using the language of vectors. So how do we describe the motion in high dimensions? Well, we describe the displacement. We specify the displacement of a particle by using the position vector r. Now we write r with a bracket t because what we mean is that the position is a function of time. Okay, so that's what we mean. Now we choose an origin, a coordinate origin. We call O. And to describe the position of the object at certain time t, we draw a vector from this origin to the object, to the position of that point object. So I denote this vector by r as a function of the time t. Okay, so that is the position of the object at time t. And in a later time, at time t plus delta t, which is a small time later, the position of the particle has changed, right? So this is the new position. And we draw a vector from O to that new position, and we call this vector R, t plus delta t, okay? Because this is the position of the particle at time t plus delta t, where delta t is expected to be a small time. We eventually will let delta t tend to 0. So we can calculate the average velocity. The average velocity is a change in displacement divided by the time taken. So we have delta r, which is equal to the vector r at time t plus delta t minus the vector r at time t. So the difference between these two vectors is, of course, another vector, right? And that vector is delta r. And from the rules of subtraction of vectors, you can see that rt plus delta t minus rt is just a vector that points from the position of the particle at time t to the position of the particle at time t plus delta t, and that is called delta r. So the pink vector is delta r. Now you can see now the important thing is the difference in the displacement, the change in displacement is no longer a number. It's no longer a certain number or certain distance. It is described by a vector with a certain direction. So the vector goes in this direction. The change in displacement goes in this direction. This is a vector. You have a vector divided by time to get the velocity. But that is the average over a time interval. So that is called average velocity. Okay. What we call the instantaneous velocity is the average velocity over a very, very small time interval. And in mathematics, we call it infinitesimal time interval. Infinitesimal means very, very small. It tends to 0. And that is the instantaneous velocity, v. And we just take limit of this guy, and we denote this guy by dr dt. R is now not a scalar, but a vector. So that is what makes higher dimensional motion different. We have a vector direction now. Now you imagine now, if this is a trajectory, the back curve is a trajectory of the particle. So you imagine delta t to be very small, then this point and this point will be very close together, right? So you imagine that the pink line that drawn up these 2 points, that is delta r, which is also in the direction of v. We become, when the 2 points are getting very close together, the pink line will tend to a tangent to the trajectory. So that is the direction of the instantaneous velocity. The instantaneous velocity is tangential to the trajectory of the particle. So at time t, the instantaneous velocity goes in this direction. It's tangential to the path of the particle, or the trajectory of the particle. Okay. And the acceleration is the change in velocity over time. So the average velocity is again defined by the change in velocity in a time interval divided by time, that time interval. And instantaneous velocity is just average velocity, average acceleration over a very small time interval and over infinitesimal time interval. So we take limit of the ratio of delta v over delta v to delta t. We take limits where delta t tends to 0, and that gives me the acceleration. Okay, that is the instantaneous acceleration. And so this is denoted by dv dt, the derivative of v with respect to t. And if you like, you can also express v in terms of dr dt, right? So that is another derivative again on v. So that gives you a second derivative of r with respect to t. So the acceleration is the second time derivative of the position. And the velocity is the first time derivative of the position. Okay, so they are completely the same, almost the same as the one-dimensional situation, except now all the position, velocity, and acceleration, they are given by vectors. Okay. Now, how to calculate that? How do we find the velocity and the acceleration by using vectors? Well, the answer is surprisingly easy, because we can denote the position on the object by its component, right? We can express the position of the object in terms of a Cartesian coordinate. And at a certain time, the x coordinate, the y coordinate, and the z coordinate, they are given by a certain function in time. Okay, suppose the x coordinate xt and y coordinate is yt and z coordinate is zt. So the position vector can be easily expressed in terms of x, y, z. We just adhere the unit vector together with x, the unit vector I together with x. We adhere the unit vector j with y, and k vector with z. We add them up together, and that gives you a vector that points from the origin to that particular position in space. That is with the coordinate x, y, z. Okay. Now, of course, x, y, z are both changing, all changing in time. So we denote it with xt, yt, and zt. And how do we find the derivative? We find the derivative just by differentiating the x and the y and the t. Okay, so we just distribute the derivative, the time derivative to each of the terms in this vector expression. The vector I hat, j hat, and k hat, they are constant. Okay, they do not affect it by the differentiation because they always take the same value. Okay, so you just have a straightforward differentiation, everything is going to work, and that is the velocity. And if you want to find the acceleration, you differentiate the velocity again. And if the velocity is expressed as vx, vy, and vz, which is this three guy actually, so if you like, you can express vx as dx dt, vy as dy dt, and vz as dz dt. And that gives you the acceleration in terms of x, y, z. The x component of the acceleration is the second derivative of x, the y component is the second derivative of y, and the z component is the second derivative of z. So that is very easy. Okay, surprisingly. Okay. Now let's handle an example that you have learned in high school, and that's a projectile motion. I think you know learn the projectile motion as before, right? And the projectile motion is described by a motion that is in two-dimensional space, but is subjected to a downward constant acceleration due to gravity. Okay. Now, in this coordinate system, the particle is projected with an initial velocity u, and u actually makes an angle of theta with the horizontal. Okay, so the magnitude of the vector u is u, and the x component of the velocity, the horizontal component of the velocity is u cosine theta, while the vertical component is u sine theta. That's you learned in high school. And because we choose the y direction to be vertical direction, so the acceleration due to gravity is always downwards, and expressed in terms of a vector is given by minus gj. Okay, j is a unit vector. Minus j is in the downward direction. Okay, that's how we express the acceleration. Okay, and of course, g takes on the value of 9.81 meter per second squared you learned in high school. That is the average value for the acceleration due to gravity on the surface of the Earth. Okay, I think you know the answer for this problem you learned in high school. The velocity, x component of the velocity is unchanged because it is not affected by any force along the horizontal direction. So the velocity at the latter time, which is vx, is the same as the initial velocity. But for the y component, the vertical velocity, vy, it changes. It is the initial y direction of the velocity vy minus gt. And this equation is simply the uniform accelerated motion in the y direction with the downward acceleration. Okay, you simply apply the equation of uniformly accelerated motion, but with the acceleration a equal to minus g. Okay. How about the displacement? Well, because the x direction is a constant velocity, so the horizontal or the x component of the displacement is simply uxt. Okay. For the y component, you again rely on the uniform accelerated motion equation. That is the uy initial velocity multiplied by t plus half at squared, right? But a is now minus g, so you now have minus half gt squared. Okay, so that completes our problem. Now you can see for the x and the y direction of motion, they are actually independent of each other. Okay, now you can see from the form of the equation. The equation in x does not contain anything in y, and the equation for y does not contain anything in x. So they are just like two motion. The horizontal motion is uniform motion with velocity unchanged, and the vertical motion is a uniformly accelerated motion. You go upwards initially, but then you are pulled down by the force of gravity. Okay, so they are independent of each other. And when the two motion combined, it gives a curved trajectory, and that's the projectile motion, just like the red line in this graph. Okay. And the two equations are connected by time. Okay, the time t is the same parameter in these two equations. And so if you want to know the position of the particle at a particular time, you put the same time in the x equation and the y equation, and you will know the coordinate xy. Okay, so that is connected. So they're connected by only the one parameter, and that's the time variable. Okay. Now this is an interesting demonstration about the independence of horizontal and vertical motion. This ball is released in red at rest, so it falls down vertically under gravity, and it's of course accelerated under gravity. So when we take the photograph of this ball in regular time interval, we can see that it is going faster and faster. So successive interval between the balls is increasing with time. Okay, so because the ball is accelerating downwards. Okay, now the yellow ball is projected horizontally. Okay, so you can see it is moving quite uniformly to the right, but at the same time, it is affected by gravity. Okay, and you can see from this illustration that the blue ball and the red ball almost has the same level, has the same height at a certain time. It's because they are projected and released simultaneously, and the vertical motion part is not affected by horizontal motion. The yellow ball has a horizontal motion, but that will not affect its falling motion. So it actually falls together with the red ball. So at any instant, you look at the two balls, they are almost at the same vertical level. Okay, and that is described by this equation. Okay, for the first ball, for the red ball, we don't have ux, so you don't have a horizontal motion. But for the second ball, you have a horizontal motion, so you have an x to be given by uxt. Okay, so that is the difference. The vertical motion, they are just the same. They are just uniformly accelerated motion under gravity. Now, that is a classical example, I think, in high school physics. I think everybody of you, if you have studied DSE physics or the equivalent level, you probably have derived it before. But let's do it again and see what are the difference. Now we are going to derive the range of a projectile motion. The range, what I mean by range is that when the projectile returns to the ground again, what is the horizontal distance between the destination and the initial point of projection? That is the range. That is called the range of the projectile. And I will show you that the range is given by u squared over g, which is initial velocity squared over g multiplied by sine 2 theta, where theta is the angle of projection. Okay. Now, so I got this result, right? I know this result from high school. Then when the trajectory returns to the ground, the vertical displacement is 0. Is that right? Because the ground is by definition of the level where y is equal to 0. So I put this y equal to 0. And that is a simple quadratic equation because I can extract a factor of t. After I do that, I can see the guy inside my bracket is uy minus half gt. And so I have two terms multiplying together equal to 0. And so either t is 0 or the term inside the bracket is equal to 0. The solution t equal to 0 is rejected because it's only specified at starting time. At the starting time, the position is, of course, uy equal to 0 because I start with the origin at the origin. So this is not what we're interested. What we're interested is the term inside the bracket. The term inside the bracket equal to 0 means the time t is equal to 2 uy over g. And that is the time when the projectile returns to the ground. Okay? And so I can use this time and multiply by the horizontal velocity ux to get the range of the object, to get the range of the projectile. And ux multiplied by this time will give you 2 ux uy over g. And I can also write ux and uy in terms of u and sine theta and cosine theta. Ux is u cosine theta, uy is u sine theta. So now you multiply ux by uy, you got u squared sine theta cosine theta. And since there's a factor of 2 here, I can make use of this trigonometric identity that 2 sine theta cosine theta is equal to sine 2 theta. Okay, now this is a trigonometric identity that you commonly use. I suggest you memorize it. Even if you don't memorize it, I recommend you to at least know that this formula exists. And so, if you are required to use it, you know how to do it. Okay, so that is a trigonometric identity. And for the cosine, if you have a cosine 2 theta, or you can either express it as 2 cosine square theta minus 1, or you can express it as 1 minus 2 sine square theta. They are just equivalent to each other. Okay. So now with this identity, I can express the range R as u squared sine 2 theta divided by g. Now, but that is only expression. That carries some meaning in physics. That must carry some meaning in physics, right? That is something that that allows us to determine how the range depends on these parameters. So we want to know what it means. Okay. Now look at this formula. Now, if I keep u to be constant, if I project the particle with a fixed velocity, with fixed speed, if the initial speed is kept fixed. But the angle, it can be varied. Okay, the angle theta can be varied. I want to ask, which angle will give me the largest range, will give me the longest range? Then I can easily draw the conclusion, because I know that sine and angle is at most equal to 1. That is the maximum value of the sine function. The sine function cannot have a value larger than 1. So the maximum value of the sine function is 1, right? So that happens when sine theta is equal to 1. And that corresponding to the angle 2 theta being equal to 90 degrees. Because sine 90 degrees is 1, right? And that gives you theta equal to 45 degrees. So that is the direction for you to have the maximum range. In the absence of area system, if you project a particle in the 45 degree direction, then you will get the maximum range. Okay, that is well known in physics, and the maximum range is simply given by u squared over g, taking where after taking sine 2 theta equal to 1. But you can have more insight on this equation. Now you can see there's a symmetric properties between the angle that are larger than 45 degrees and smaller than 45 degrees. And so you can easily see that the range at theta is actually equal to the range as 90 degrees minus theta. Okay, how do you know that? If you substitute 90 degrees minus theta into this equation in the place of theta, you will see sine 2 90 degrees minus theta is actually sine 2 theta. Why? Because 2 times 90 degrees minus theta is 100 degrees minus 2 theta, right? 100 degrees minus theta is actually in the second quadrant. Is that right? 90 to 180 degrees is a second quadrant. And so 180 degrees minus 2 theta is like the angle is actually in the second quadrant. So that is positive for sine. Okay. And so sine 180 degrees minus 2 theta is actually sine 2 theta. And so that's why there's a symmetry. With the angle theta equal to 30 degrees, gives the same range as the angle 60 degrees. And with theta equal to 15 degrees, it just gives you the same range as the angle 75 degrees. Okay. So they are symmetrical about the 45 degree maximum range. Now, so that is what different from you did in high school. In high school, you are always given some numbers. Okay, when teachers tells you to do something, she or she always gives you some numbers, the angle, the speed, and you need to find a range after some massive calculation with those numbers, carrying those numbers around, and you find that the range is 40.8 meter. Okay, so that's what you done in high school, right? And in high school, you got an A because you know how to do that. But for university study, we don't normally rely on particular numerical example. We want to make it general by expressing the quantity in terms of the variables. Okay, we express the R in terms of U, in terms of theta, in terms of G, so that whenever any of this quantity change, you know how R will respond, how R will change accordingly. Okay, so that is the idea of learning physics. You know the dependence of various quantity. You know how the change in one quantity may affect another. That is important. That is the important message you got from the equation. Okay, so after you got this formula, and you're given a particular numerical example, you can substitute all those numbers into this equation and you get the result. And if you present it this way, you got an A for this course. If you start up with a messy calculation with numbers, you probably will get only a B+. Now, so what is the advantage of doing a symbolic calculation? As I say, it gives you an insight of how various physical quantities are related. Okay, so if somebody asks you, well, what will happen if you increase the speed of projection? If you double the speed of projection, what would be the change in R? Then you immediately realize that because it's U squared, okay, it's square of U, but not U, that appears in this formula. So when U doubles, then U squared will be 4 times as large, right? Because it's 2 U's, you take the square, it will have the factor of 4. Okay, so you know that the range will be 4 times as large, but not just double. So you immediately know the dependence. Okay, so that allows you to draw the general inference about the motion. How the R depends on U, depends on theta, and depends on G. If somebody asks you, how about doing this experiment on Mars, on the surface of the planet Mars, but not on Earth? So you can look at the acceleration due to gravity on the surface of Mars, and you substitute it into this place, and you get the range on Mars easily. Okay, and so that allows you to predict the new outcomes when the parameter change. So in effect, you are not solving only one problem, but you solve a whole range of problems, and that is a very general. Okay, and that allows you to apply the situation, apply the formula to different situations. So you solve a whole range of problems instead of just one problem. Okay. Now, so we can also derive the equation for the trajectory of the projectile motion. Now, we say that the horizontal motion and the vertical motion, they are connected by parameter time. But we can actually eliminate that. The easiest way to eliminate that is to look at the x equation. We can express the time t as a subject of the formula. T is equal to x over ux. And so we can substitute this x into, substitute this t into the equation that describes the vertical motion. Okay, so we put the t here to be x over ux, and the t squared here we also replace by x over ux. And after some simplification, and with the substitution ux equal to u cosine and uy equal to u sine, we got this formula. Okay, so uy over ux is sine theta over cosine theta, and that's give you tangent theta. And ux here in the denominator become u squared cosine squared theta, right? So that's with the trajectory equation we found. Now, it looks rather scary when you look at this equation at the first time. It looks quite scary, but imagine what is that? What this equation means for you? It is the relation between the horizontal position and the vertical position. So it relates x and y, and that gives you a curve in the xy space, and that is the trajectory of the particle in the projectile motion. Is that right? So you don't be scared by this tangent, this complicated g over u squared cosine theta. They are the constant. Okay, the variable are x and y, and this equation describes a relationship between x and y, and so that is describe a curve in the xy plane. So we may write y in as the following. It is a constant a multiplied by x minus another constant b multiplied by x squared. And as soon as you write it down in this way, you realize that this is a parabola, right? That is a parabola you learned in high school. And the parabola concave downwards. It starts from the origin because when x equals 0, y is also 0. And it's also concave downwards. It eventually will fall back to the ground. Because the term with the coefficient, the quadratic term x squared has a negative coefficient. So it's curved concave downwards. So it's like this. Okay. Now this is a famous problem in high school that I think you might learn in high school. That is called the monkey and hunter experiment. In high school, you may be given some number to substitute in the equation and to verify that when the monkeys fall, during the firing of a bullet at the monkey, Then after some time, the monkey will meet the bullet again at some places below the point of falling. Okay, that is a monkey and hunter problem. This problem says whenever you aim the gun at the direction of the initial direction of the monkey, and you fire at the same time as the monkey begins to fall, then the bullet following a projectile motion will eventually hit the monkey at a certain position in its falling motion, no matter where it is, as long as you fire the bullet at the same time when the monkey is released. The bullet will always hit the monkey. Okay, so that is interesting. Okay, I'll give you a video to see that. The people in the MIT, they create an interesting video on this monkey and hunter experiment. So I allow you to have a full screen view. So that's maybe I share it again. I forgot something. Okay, that's fine. So there's an electromagnet released at the top. So as soon as the golf ball is fired, the monkey is also released at the same time. Slow motion again. Okay, so with some sound effect to mimic the crying of the monkey when being heated. So that is the idea. Now, you may wonder why this happened. The teachers in high school probably give you some number to plug in to see this actually happen. But I want to prove it generally. Okay, that happens for whatever initial velocity and whatever distance you are from the monkey, as long as you aim at it in the initial direction and you fire the bullet at the time when the monkey falls, you always hit the monkey. Why is that? Now we start from the equation for the uniform motion. Okay. Now we write it in terms of position vectors. The position vectors now has two components, the x component and the y component, and we are here unit vector with it. Okay. So we just copy the result. This is the x component, so it's uxt I. The y component is uyt minus half gt squared. Is that right? Now we gather the term with the u. Uxi plus uyj multiplied with t, right? So we gather the two terms with ux and uy. We put it together. And the last term that consists of half gt squared, we put it alone. Now we immediately realize the term uxi and uyj is just the initial velocity u. Is that right? Because the x component is of the initial velocity ux and y component is uy. So of course, if you add the unit vector here, the unit vector to this two and add up together, they just give you the initial velocity. So I have the initial velocity multiplied by t minus half gt squared. And this term, the last term, is in the direction of minus j. Okay, and that describes the motion of the bullet. Okay, the motion of the bullet is described by this equation. So let's look at what happened here. Now, so how do we know when the bullet will hit the monkey? It's easy. Now we wait for a certain time t. Now we can look at this expression. R is given by u vector t minus half gt squared. We can look at it as an addition of two vectors. One vector is ut, and another vector is minus half gt squared, which is vertically downwards. Okay. Now we wait for a certain time. We know that that will happen. The initial velocity is pointing towards the monkey. So whenever we wait for a certain time t, the initial velocity will carry the bullet to the position of the monkey, and that is described by this vector we call ut. Okay, you simply divide this distance with u, and you will get the time that the vector ut will point to the initial direction of the initial position of the monkey. Is that right? But it's not the whole thing. Ut is added to minus gt squared. So minus gt squared is just a free fall distance in a time t, right? So the monkey fall downwards by half gt squared. So the two vectors added together to give the red arrow, which is the direction, which is the final position of the bullet. Is that right? Now, but at the same time, the monkey falls vertically downwards by the same distance of minus half gt squared. So it always meets the bullet here. Okay, no matter what, right? As long as you initially pointing the bullet, the gun towards the monkey, it will eventually hit the monkey at a distance half gt squared below the point of suspension. Okay, so the idea is easy. How do you find the position here? You just divide the distance between the hunter and the initial position of the monkey by the initial velocity, and you get the time. The time for ut be equal to this vector, right? And you use that time and you substitute into half gt squared, you get the position where the bullet hit the monkey. Now, so when you use vector, you see that simplifies a lot of calculation. You don't need to do any calculation, and you immediately see why it will hit the monkey. Okay, and that is a miracle. I think, I mean, not a miracle, but something that is worth looking. That is interesting. Okay, so vector actually simplify a lot of calculation. When you use vector, all the difficult things are hidden somewhere, and the angles and all those discussion, all those projection, they're hidden inside the vectors, and so you can express the results very nicely. Okay, and you can see that that result is true very easily. Then we will discuss a very important part of our course, and that is circular motion. Okay, I think you also learned circular motion in high school, but perhaps you learn it using the language of drawing picture to derive the centripetal force. But now you are using vectors to do the same derivation. Now we described a uniform circular motion by using a position vector r. Okay. Now this red dot, it goes around in a circle around the coordinate origin on the xy plane. Okay. So the radius r is fixed. So we better express the position of the particle in terms of this angle. This angle is called theta. Okay, r is fixed and theta is changing with time. And for a uniform circular motion, this angle increases linearly with time because the motion is even. The point will not move faster and slower at different time. So the angle will increase evenly with time. And so that's given by linear relation. Okay. The linear relation is a constant or called omega multiplied by the time t. Assuming initially t equal to 0, the particle is on the x-axis. So the angle here increases linear with time as omega t. Where later we will find that omega is actually the angular velocity or the angular speed. Okay. So that describes a uniform circular motion. Now, important thing to note that is that although the distance r that the particle from the origin is a constant, but the r vector is not a constant because the vector points from the origin to the position of this particle. And that vector is keep on changing with time because it's changing direction. As the angle theta increase, the vector change direction, right? So the r vector is not a constant. But the magnitude of the r vector is a constant because the magnitude of the r vector is a radius. And for circular motion, the radius, of course, is a constant. So you should know the difference. So how do we specify the displacement? Well, we resolve the r vector into two components as before. The x component is r cosine theta. And now theta is omega t. So we have r cosine theta or r cosine omega t as the x component. The y component is r sine theta or r sine omega t. So that is the y component. We add the two components together. We express everything in terms of omega t. And then we should remember to put the basis vector. The I is for the x component. The j is for the y component. Okay. So how do we find the velocity vector? We find it using a straightforward differentiation. We just differentiate with respect to time and we get the velocity. Okay. If you differentiate a cosine omega t, we have discussed with you before of how to do it, right? We use chain rule. We differentiate the cosine with respect to omega t first, and that gives you a minus sign. And then you differentiate the omega t with respect to t, and that gives you a factor of omega. Is that right? So after doing it a few times, you will soon realize that the differentiation is nothing, but you turn the cosine into a minus sign, and you have an additional factor of omega. Similarly, if you start from a sine for the y component, you turn the sine into a cosine, and you have an additional factor omega. So you can pull that additional factor omega out, and you have the combination omega r here together with this vector. Okay. So that is a trick. You always turn the sine into a cosine and a cosine into a minus sign. And in doing so, you remember to pull a factor of omega out. Okay. Now, so what is this? This vector looks a little bit scary, right? But it's a unit vector anyway. It does not carry a magnitude. Its magnitude is 1, right? How do we know that? Because this is sine square, right? The magnitude of this guy, is what? Is minus sine omega t square plus cosine omega t square, taking square root. Is that right? But cosine square plus sine square, the minus sign gone because of I take a square. Cosine square plus sine square is 1. So this is 1, right? So this guy does specify the direction. It does not specify the magnitude. The magnitude all goes here. It all goes to the omega r. And if I equate the magnitude of the vector on both sides, I got v equal to r omega. Is that right? If I consider only the magnitude but not the direction, what I got is v equal to r omega. But that is what you learn in high school. That is a relation between the linear velocity and the angular velocity. Omega is actually the angular velocity of the circular motion. And if you multiply the angular velocity with the radius, you got the linear velocity of the particle, right? So you derive the circular motion result. And how about the velocity, acceleration? You differentiate the velocity once more, okay? Now you turn the sine into a cosine, and you get additional factor of omega. So you already have one omega and you now got another omega. So you got omega squared. And you can pull the minus sign out. And for the cosine term, you differentiate it, you get the minus sign term and also 2 omega. But a cosine become minus sign, you have a factor of minus negative sign. You pull the minus sign out together with that of the first term, and you get minus omega squared r. Okay, multiplied by cosine omega t I plus sine omega t j. But what is that? R multiplied by this guy is simply the position vector, right? You can realize that this is a position vector. So the result is that you can write it as minus omega squared r, where A and R, they are both given by vectors. Okay, R is the position of the particle given by vectors, and A is the acceleration of the particle also given by vectors. Now, so what does this equation means? It means everything you learn about circular motion in high school. Because I don't go. Now look at this. If I take the absolute magnitude, on the left-hand side, I got the acceleration. And if I take the absolute magnitude on the right-hand side, I simply got omega squared r. But what is that? That is the centripetal acceleration, right? The centripetal acceleration you learn in high school is given by omega squared r. And if I like, I can change it into v. If I express omega squared as v squared for r squared, that gives you v squared over r. That is the centripetal acceleration. So after 2 differentiation alone, you got the centripetal acceleration. The direction is also correct. You can see the r is pointing outwards, right? It's pointing outwards from the origin to the particle. But the A here is in the direction of minus r. So that means the acceleration is in the opposite direction to the radial vector r. So it is pointing towards the origin, which is the center of rotation. So that is the centripetal acceleration, because the acceleration is pointing towards the center of the circle, right? And that is what you learn in high school. You already derived them all here in just 2 lines, okay? So you can appreciate that powerful analytical method. After 2 lines of differentiation, you got everything, okay? Now, you may be puzzled by what this vector means. What is the direction of this vector? I will let you see the direction. I form a dot product of R with V, okay? R is given by, of course, given by this vector, and V is given by this vector, right? I form a dot product between the two. And I have omega r squared, that is not important. The dot product between these 2 base unit vectors are important. Now I have I dot I equal to 1. So for the first term, I have minus cosine omega t sine omega t. I dot j is 0. J dot I is also 0. So I don't have the cross term. And the term j dot j give me 1 again. And so that gives me sine omega t cosine omega t. And so you have minus cosine sine plus sine cosine. And that, of course, is 0. So you have 0 as a result. What does that mean? R dot B equal to 0 means r and v are actually perpendicular to each other. So if you have the vector r pointing radially outwards, then the vector v is just perpendicular to that vectors, and that means the velocity v is tangential to the circle. Okay, and that's of course is the case for circular motion. And you can figure out that this particle is going in an anti-clockwise direction by looking at the direction of the velocity at time 0. You will find that the direction is upward, it's in the y direction. And so that means the particle is going around in this direction. Okay. So again, let's summarize. From this omega r and v, we got the relation between the linear velocity and the angular velocity. And we also find the acceleration in terms of omega and r is given them in magnitude by omega square r. And it's in the inward direction, is pointing towards the center. So that is a centripetal acceleration. Okay, so we prove everything. Okay, everything finished in just 10 minutes of discussion. Okay. Now let's look more closely at the so-called omega or angular velocity. The sine function and the cosine function, they repeat itself after 360 degree, or in radian that is 2 pi, right? And what we mean by period is that the particle will returns to its initial position after a period. That is called a period, right? So that means when the time t is equal to the capital T, which is a period, then the angle being described by omega t will go through a change of 360 degree or 2 pi. Is that right? Because 2 pi means a whole circle. Okay, and it means the sine function and sine function returns to its initial value. So that must be corresponding to a period. So that means omega big T is equal to 2 pi. And we have the angular velocity being equal to 2 pi divided by the period T. Okay. You may call it angular speed if you ignore the direction. If you don't care about the direction clockwise or anti-clockwise, you may call it angular speed. And that is the angle in radian traveled by the particle per unit time. Okay, so that is the physical meaning. The angle divided by time, the angle change divided by time is the angular speed. Now you can also define the linear frequency. The linear frequency is the number of cycles per unit time. Okay, and the frequency is related to the period by the reciprocal. 1 over the period t is a linear frequency. So you can easily see that the frequency, the linear frequency and the angular frequency, angular velocity or angular speed, they are just related by 2 pi. The angular frequency divided by 2 pi give you the linear frequency. The linear frequency gives you the cycle, the number of cycles per unit time. Okay, so if you have a period, if the particle go through a period in say 2 seconds, okay, then that means in 1 second the particle just go through half of a cycle. Okay, so the frequency is 1/2. Okay, so that is how the frequency and the period are related. Okay, if the particle go through 3 cycles, say 3 cycles in just 1 second, then the corresponding period is 1/3, 1/3 of a second. Okay, so that's why the frequency and the period are reciprocal of each other. Okay. Now let's go 3-dimension. Going 3-dimension is not that difficult. You can just add the k vector. Okay. Now this is a circular motion that we have just derived. We confine ourselves to the circular motion in the xy plane, right? The particle moving uniform circular motion around the origin on the xy plane. Now we add a z component, and that turns a 2-dimensional motion into 3-dimension. The particle now has a velocity that goes in the z direction. Now, what does this vector describe? Okay, I skipped something, but let's describe the three-dimensional thing first. Now, this vector is actually UT. Now, UT actually means a uniform motion in the Z direction, right? Because the displacement increased linear with time means a uniform motion in the Z direction. Now, how can we imagine that? We have a circular motion in the XY plane, but that is added to a motion, a uniform velocity motion along the Z direction. When you imagine the two motions added together, that becomes what? That becomes a helical motion, a motion of a helix. Okay, just like helix, just like you have some screw, and you turn your screwdriver around in a certain direction, the screw will advance forward in a helical path. But what is that motion? What is a physical example for that motion? If you have a charged particle in a magnetic field, you will have that motion. Now, in your high school, you always have the charged particle. What you learn is that the charged particle is projected in the direction parallel to the perpendicular to the magnetic field. In that case, you only have a circular motion. But now you suppose the initial velocity of the charged particle has a component parallel to the magnetic field. That component is u, okay? That velocity will not affected by the magnetic field because when the motion of the charged particle is parallel to the magnetic field, that will not produce a magnetic force. So that component will not be affected, but the perpendicular component of velocity will be affected, and it goes through a circular motion. The parallel component will just continue as it is with a uniform velocity, and that gives rise to a helical motion. Okay, so that turns you into a three-dimensional world. Now, where this motion happens? Actually, it happens in the magnetic field of the Earth. You know that the Earth is a giant magnet, right? It has a magnetic field lines that goes from the South Pole to the North Pole. Okay, so that goes like this. And when the magnetic field of the Earth traps the high energy charged particle from the sun is giving out electron and proton at high speed. There's some so-called coronal ejection, and those are the ejected particles from the surface of the sun. And several hours later, they will reach the Earth, and part of this charged particle will be trapped by the magnetic field of the Earth, and it will gyrate along the field lines. And when it meets the North Pole, for example, the density of field line gets higher, and it will bounce back. Okay, so that it will gyrate along magnetic field lines and bounce back and forth between the North and South Pole. And when some of the particle goes into the atmosphere on the Earth, it collides with the air molecule there and excite them, and so that gives rise to a colorful aurora, 極光. That is the origin of aurora. Okay, so that is a story of how the charged particle are trapped by the magnetic field of the Earth. Okay, so that is a 3D example. Now we have a classwork for you. That's a simple classwork actually. For the circular motion that we have discussed, we have this position vector, right? Then that position vector describes a circular motion. When we are looking from the top, when we're looking from the Z axis, circular motion is in the anti-clockwise direction. So how can you write circular motion for a particle that rotates with the same angular speed, but now in the clockwise motion, in the clockwise direction? How do you do that? How do you reverse the direction from anti-clockwise to clockwise? Anybody tells me? The answer is very easy. You simply turn the omega here is positive, right? You simply turn this to be negative. Instead of having a positive omega t, you deliberately add a minus sign to denote that it's negative, okay? If you write this, that means now the angle is given by minus omega t, where omega, of course, omega is not, sorry. I make a double negative. Well, the quantity omega, I make this, I define it as positive. So the minus omega is negative, okay? So the angle is increases to the negative side. So the particle actually rotate in the clockwise direction. Now, if you like, you can simplify it. Cosine negative angle is just a cosine. So it remains the same. But sine and negative angle become minus sine omega t. So that describes a circular motion in the clockwise direction. Now, somebody asked me, what is the meaning of UT? UT is a uniform motion, right? Do you remember your high school physics? Sorry, I go back. What is the meaning of this? This is a uniform motion in the x direction with a velocity u, right? So this term means you now add the whole thing to a uniform motion in the z direction. Now, this two terms is a circular motion on the xy plane. Now you add the motion in the z direction. So that turns a circle into a helix. Is that right? Okay. Now, I prefer not to keep you so long. I prefer to leave this to the next lecture. Now, this is nothing but the proof you encounter in your high school study. We simply have the velocity at different times, slightly different times to be given by these two velocity, and we find a difference of the velocity delta v. And in limit delta t over delta t tends to 0, that gives you the acceleration as r of omega squared. But we are going to discuss it later. I think you already have learned it in high school, so I will not be repeating a lot. And I just want you to appreciate how powerful the analytical method is. In this proof, you have to look at the angle, right? And you have to look at the angle that the two velocity has changed, and that's equal to the angular displacement of the object. And eventually you have to divide by delta t and take the limit. Okay, but with the vector formula sum, you don't have to think. You just differentiate. Okay, so that is the difference. Now, so I better stop here. I don't want to hold you for too